You will remember from Friday, right? Friday, I ranted about the difference between models, theories, and laws. And as I sat there and watched that video of the plant, I thought to myself, what are they doing? They're explaining how, for example, the mimosa plant, what did it say happened there? That was the one where you touched it, electrical signal, and it curled up, right?
Yeah.
That was the explanation. That is the theory. Well done, Jason Pitch. That is the theory. That is the explanation. So if I asked you again today, what's the difference between a model, theory, and a law? Could you tell me? By the way, those of you that have laptops, like I'm gonna give time to get a period. Okay? I'm not gonna do all periods, so there's okay? Because everyone has to do it. So what's the difference between a model, theory, law? You'll remember that on Friday, I had you do this front page here. You kind of told me what you thought. Most of the time, and you guys weren't the exception, people think that theories are unproven laws. Not true. In fact, it's, what is the word? Rubbish. You were right, Anna. Rubbish, right? Garbage, right? And I ranted on and on about that. You were like, oh my God, will he ever shut up about it? Okay? Well, here I am back talking more about it today. Okay, now you should have a little booklet there of stuff, right? Can I see yours? So, yeah, just look at yours for a second. Okay, so what I'm going to do today is I'm going to read this here, just in case maybe you didn't quite either A, believe me, or B, understand. I'm going to kind of reinforce some of these things. Then there's one for you to read with a few little questions. And then we're going to tell you a cool story about a smart horse, and we'll likely have time to do a couple fun things at the end as well. I need to find my copy of that so that I can read it. Oh, did you know that today is International Talk Like a Pirate Day? Did you know that? International Talk Like a Pirate Day. Did you know, Zoe? You know what a pirate's favorite letter is? You think so, but he really loves the sea. Thanks for playing along with me. I knew I could always count on someone to think they got me. But seriously, today is International Talk Like a Pirate Day. Okay, so I have this one here that says models, laws, and theories. I would encourage you to have a highlighter, maybe a pencil, something that you can sort of, that's not the one, or is it? Nope, not the one.
Yeah.
Okay. I would encourage you to do little highlights or what have you as we're going through this. Okay? So, science is more than just a collection of facts and observations. Models, laws, theories, and evidence, that's one word that isn't on the board, all play an important role in understanding the nature of science. A scientific model is, oh, that sounds like a cue, like a definition, right? A scientific model is a conceptual representation or idea in your head that stands for and helps explain other things. It can be physical, imagined, or even mathematical. Right? It's a way of describing something that is hard to describe. Quite often it's physical. An example of a physical model would be a globe, or the Bohr model, or those little molecule models that you play with, right? Chemistry class. What would be like imagined scientific model? I guess the Bohr model might be more imagined, right? You draw it on paper, but it's sort of more of an imagination kind of thing. In science, we develop models that have explanatory and predictive powers, like the model of the universe. What do I mean by explanatory? The model is able to explain. Predictive, it's able to do what? make predictions about something that's going to happen in the future. And we see that over and over and over again. Einstein predicted. Let me explain right away. Hello, Mr. Robinson. I think so, yes. Hannah? Yeah. Sure, okay. Yeah. Look at green. Okay. Okay, so predictive powers. Einstein theorized about gravitational waves. This was in the news a few years ago, right? And then just recently they actually discovered them. His model, his theory was predictive, and then later we discovered that it was true. We test these models in the world around us. If our model predicts our observations, we accept the model as a valid description of our world. We say, that model is a good one. It worked. If our model encounters discrepant events, ooh, that's a big word. What do you think discrepant means? I'll give you a word that's similar to it. Discrepancy. What's a discrepancy? It's like a mistake. Like, for example, if I'm marking your test, and this will happen, by the way, and I make a discrepancy, I make a mistake. Maybe I add up your marks incorrectly, right? And you got 20 out of 25, and I said you got 18. Well, that's a discrepancy. Maybe you're a few hours short of work. That's a discrepancy. Okay? So a discrepant event is an event where there's a mistake. So if our model encounters discrepant events, in other words, things that don't fit, things that don't match up, and fails to provide adequate explanations, we begin to modify our model or search for an entirely different model. Okay? If it doesn't make sense, we start to modify. A good example of a scientific model is the model of the solar system. Some of you are already highlighting it because you recognize that it's something that should be done. Right? The old sort of 9 planets, used to be 9, now it's 8. At one time it was thought that the sun revolved around the earth. When you get up in the morning and you watch the sun go across the sky, it's pretty easy to understand the people from ancient times thinking, oh yeah, well, there's the sun going around us, right? It makes sense. At one time it was thought, okay, and this geocentric model, geocentric means earth at the center of the universe, was considered to be a true representation for many centuries. The model encountered a discrepant event, something that didn't make sense, when the retrograde motion of the planets did not exactly fit the epicycles of the geocentric model. When did Mr. Bennett stop speaking English? Oh, not that long ago. Retrograde motion. What does retro mean? Old, right? Vintage, something from the past. Retrograde motion means something that goes backwards. So this retrograde motion is something that goes backwards. Did not fit the epicycles of the geocentric model. So here's how I'm going to explain it. I'll do it up here in the morning. So if you've got Earth here at the center, okay, and the planets also revolve around the Earth, then they should look, for us Earthlings, it should look just like a big circle, right? You look up, you see the planet going across, and the next day it's just like the moon. But the problem is the planets don't do that. In fact, the planets do this. As you watch them in the night sky, can you recognize planets in the night sky? Do you know how? Maybe grade 9 science? How do you recognize the planets from the stars? There's a couple ways. They are bigger, they're brighter, right? They don't twinkle, and they also tend to move weird. You watch the constellations, and they move uniformly across the sky, but the planets actually, as they go across the sky, go like this. And that's that retrograde motion. They kind of back up, but they go back the way they came. In fact, the word planet comes from the Greek word planetos, which means wanderer, because the planets wander throughout the constellations. Okay? So this geocentric model, with the Earth at the center, couldn't explain that. Why would these planets really be backing up and going around like that? It didn't make sense. And so a bright guy, anyone know who is known or thought to be the first to say the sun was at the center? Anyone remember? It's not Galileo. Nobody knows? You do know, you're just too shy. You know? Huh? Copernicus? Copernicus? Doesn't ring anything about? Nikolai Copernicus, I think he was Danish. I don't mean something after breakfast. Okay? He was the first to suggest, I believe. I believe there were scientists prior to him, but he was sort of the guy that sort of made it popular. Went viral, you could say. Okay, so the model, the geocentric model, encountered a discrepant event when the retrograde motion of the planets did not exactly fit the epicycles of the geocentric model. A new model, the Copernican sun-centered model, there's the answer right there. The sun-centered model provided a simple explanation of the movement of the planets, and it predicted the phases on Venus. What the heck does that mean? So Copernicus' model made sense why the planets were doing that retrograde motion. It put the sun at the center, and this whole idea of phases on Venus. When you look at the moon, okay, here's the question for you. When the moon is like a half a moon, is there less gravitational pull? Why not? But there's only half a moon there. Still there, absolutely it's still there. You just can't see it, right? Those are the phases on the moon. You know that quarter moon, half moon, three-quarter moon, full moon? Those are called phases. Did you know, if you look at Venus, there's phases on Venus as well. How come we don't see them here on Earth? Because Venus is teeny tiny. You can hardly see it. It's actually pretty big. You can see it, right? You can't see when it goes past Venus. So Copernicus predicted the phase on Venus, and then when they invented the telescope, they looked and they went, oh, hey, that Copernicus dude was right. His model must be right. Okay, so it predicted. These are wonderful examples. Observations can be used to test models, both externally or by thought experiments, as we rethink and apply our model to new and sometimes discrepant situations. Our observations can lead us to identify regularities and patterns in nature. We call these regularities and patterns scientific laws. It's the law. For example, a simple scientific law would be what goes up must come down. I throw the marker up, and lo and behold, it comes down. Every single time. In one of these years, I'm going to develop my Jedi powers and make that marker stay up there. But I haven't fully got it yet. All right, it's the law. Whatever goes up has to come down. It's a regular pattern. It always happens. We can also deduce laws given a certain set of conditions. For example, if light is a wave, we can geometrically show that the ratio of the signs of the angles of incidence and refraction is a constant. You don't need to know that. It's known as Snell's law. We can often represent laws as mathematical relationships, linear relationships perhaps. Snell's law, Ohm's law, Charles' law, or Newton's laws. All right, those are all laws that are patterns. F equals ma, that's a pattern. Contrary to popular belief, laws are not absolute. What the heck does that mean? Laws are not absolute. It means that they are not always true. Only true under certain conditions. Okay? Ohm's law is valid only for some material, and our pressure laws are constrained by temperature. Even Newton's laws are valid only in inertial frames of reference. There are certain restrictions to the laws, like exceptions. Scientific theories form explanatory systems for phenomena. Oh, that is important. And, don't know what? Woody. Scientific theories form explanatory. I wonder if Ted Ed would like my coloring. Sorry. Scientific theories form explanatory systems for phenomena. They explain the law. Theories explain the law, maybe. Let's take the jacket off. Stay a while. Not too hot. Sitting there with your jacket, looks like you're sitting in the rain. Not hot. Scientific theories form explanatory laws of phenomena. They explain the laws and may include presuppositions, models, facts, and laws. So in other words, theories are like the big giant paper, the whole PowerPoint, and all the other things, the models, the laws, are sort of like parts of that. Okay, does that make more sense for you? I know it's not particularly exciting. I'm trying to make it as entertaining as I can. With my color, yes. For example, Einstein's theories presuppose that the speed of light is constant in all frames of reference. Einstein's theories assume that the speed of light is constant. Anyone know what that number is? I do. I'm a nerd. 3.0 times 10 to the 8 meters per second. It's really fast. In Einstein's world, Newton's laws, such as F equals ma, hold only for objects that are moving much more slowly than the speed of light. When you speed things up, Newton's laws don't apply anymore. It's kind of weird. When you speed things up, gravity changes. Time changes. A lot of weird things happening now. We must be very careful about how we use the term theory. Okay. Star. Because when you came into class the other day, most of you, thought that theories were simply laws that weren't proven. I showed you a video of a politician who used the phrase, what did he say? Just a theory. And he basically showed the world that he doesn't know the difference. Okay, in everyday usage, the word theory often refers to an idea that's not proven. In everyday usage, walking down the street, talking to grandma on the street, they think theories are things that aren't proven. That's the everyday usage. In science, not true. It's partially true that some theories that make cosmological theories are speculative and are based on little bit of evidence. I'm going to make a note about this right away. Additionally, children often hold simple or naive theories about why things float or why the sky is blue. Hypotheses or proposed solutions are often speculative. We often seek to build support for them through predictions and observations. However, other theories, like theories of radiation, metabolism, chemical bonding, have considerable evidential support. In other words, those theories have a lot of evidence to do what? Back them up, to say that they are true. It is impossible to prove our theories for every possible case. But robust theories explain a great deal, and we sometimes literally bet our lives on them. Therefore, scientific theories lie along a spectrum. What's a spectrum? Spectrum of color. Roy Jabib, right? The rainbow. The spectrum is like the whole left to right. Lie along a spectrum form speculative hypothesis to robust explanatory systems. Okay. I want you to, at the bottom of your page, you have a little bit of room? Just a little bit? I want you to write two words. I want you to write speculative.
Are you going to make this possible?
No, promise. This is true. And you're going to have a line, and then you're going to have robust. But you do need to know, I'm going to put it on the board. This is something you need to know. Know the difference between robust and speculative theories. Now, I've already explained it, but I haven't done a very good job. What is a speculative theory? It is a guess. It is the starting point. It is the bare bones explanation. And then as more evidence is gained, as more and more experiments are created, more and more people are jumping on the bandwagon, the theory becomes robust. It has a lot of meat to it, right? It's like a hearty, thick stew. It'll stick to your ribs. It makes a lot of sense. Speculative is kind of thin. It's like, the beef consomme soup. Just broth, nothing in there. You're going to be hungry after that. Okay? So speculative theories, as evidence is gained, become robust theories. But they are still theories. They never ever become laws. Laws are what we observe, the pattern. And the theory is the explanation. Is it starting to gel for you? I hope so. Guaranteed it'll be on the test. Explain the difference between a theory and a law. Explain the difference between a robust theory and a speculative theory. Guaranteed. You'll get a sad face if you write, theories are unproven laws. You get a frowny face. A little bit more to read? I think so, right? Okay. I'll wrap up soon. In science education, we often use early models or theories that are adequate for a less sophisticated understanding of a scientific concept. In other words, we tend to teach, we tend to teach kids, younger kids, even yourselves, not so much speculative theories, but less robust ones. We sort of pare back the degree of difficulty. And then as you get older and more have a greater understanding, you get more and more to robust theories. For example, I hate to tell you, Bohr's model of the atom explains all the phenomena that one might examine in an introductory chemistry program, but it's not entirely true. More progressive theories require a more extensive backup. So you sort of graduate up to more the shell theory. You guys done the shell theory in chemistry yet? With the shells that overlap? Some of you have, right? P and the S and all that stuff, right? While it's important that our understanding of the nature of science is embedded in the context that the world is rational and can be understood, we never really know if we have achieved the most rational explanation. In science, the truth is elusive. In other words, it's hard to find. But our beliefs must extend far beyond individual opinions. We must insist on evidential argument. Okay? Science insists that you literally show me the money, like the movie says. Show me the evidence. Okay, so there's a lot of controversy about climate change theory. What is climate change theory? What do most scientists believe is driving climate change? Humans, and pumping more carbon into the atmosphere. There's also a lot of deniers, and they like to use things like, well, it's just a theory. Oh, you need an explanation of what's happening? You're absolutely right. Is there evidence for it? Tons! Is it more controversial than it should be? In my humble opinion, yes. Okay? Now, it's for you to make up your own mind. I'm not trying to make you create your own opinion, but I do want you to think about evidence and theory, and don't you dare, I will be mad at you. You go out there, if you become a politician, and I catch you saying just a theory, I will go to your rally, and I will mock you, and I will make you cry. Okay? And I will say, don't you remember back in 2017 when I taught you the difference, right? So watch out. Okay, a little bit more. One of the main questions scientists are concerned with is the relationship between theory and evidence. It's not unusual in science education to make a knowledge claim in the form of, I know that, I know something. For example, while discussing health with your doctor, she might say that lowering cholesterol level lowers one's risk of heart disease. To further the claim, support is found for that knowledge claim. We call this support evidence. The nature of evidence presented will depend on the background knowledge of the knowledge claim. In other words, if you go to the doctor, guys, you really got to listen. Because if this is the way it's going to be in physics, guess what? It's going to be a struggle. Seriously. I've been through this many, many semesters. I know how it goes. You got choices. And you're making a bad one right now. This whole bit here. When you go to see your doctor, if it's a general practitioner, sort of the person that you go to see for many different things, they may send you to a specialist. They're not as versed in that, right? And so the information that they give you might be sort of more generic. That's okay, right? That's the nature of the knowledge claim. For example, this doctor might stress that the statistical evidence or discuss the latest hypothesis of the underlying mechanism that relates to cholesterol level and point formation. Nobody knows what that means. Of course, one might simply quote a recognized authority like the Department of Health and not attempt to formulate an argument at all. Your doctor, you might just believe them because, well, they're a doctor, they went to school, you're not. You should listen to them, right? But could the doctor be lying? Certainly. On purpose? Not likely. Could there be fake doctors out there? Yes, in fact, I just read that the other day about some guy that he wasn't a doctor, he was a lawyer, claiming to be a lawyer, was doing all this stuff, had no law training whatsoever at all. Be wary, be cautious. Since the background knowledge of the claimer and the intended audience may be different, an evidential argument must be given that makes sense to the audience and connects with their prior knowledge and experience. I have to explain things at your level. When I go back and teach grade 10 science, I have to go kind of downshift a little bit and explain things to grade 10 level. When I explain things to grade 12, I step it up a bit. I have to remember where everyone is. It's a hard thing to do as a teacher, actually. Consequently, a selection process or theory choice is involved in deciding the adequacy of a given theory in terms of the ability to accommodate the available evidence. There's a lot of big words in this thing, aren't there? Aren't you glad that I'm explaining it as I go and not making you read it on your own? This selection process reviews and judges the characteristics of a good scientific theory. A good theory, this seems like something that's important. It's not. A good theory is accurate, which means that the predictions that the theory makes closely match the observations. If you observe something, and then the theory explains it, and it matches, well, then that's good, right? The theory with the Earth at the center didn't match the observations of the planets, so it wasn't a very good theory. There's my crazy coloring again. However, accuracy is not the only characteristic of a good theory. When two theories are equally accurate, the better theory is often the simpler explanation. And I'm going to hopefully tell you a story about that right away. The simpler one. The Copernican model of the solar system was no more accurate than the Ptolemaic model, with a series of epicycles to account for the motion of planets. In fact, a guy by the name of, was it Tycho Brahe? No, it was Kepler. Kepler wrote a whole bunch of crazy mathematical formulas that explain all that crazy loop-de-loop kind of motion. But it was very complicated. So Copernicus put the sun at the center and said, hey, a lot simpler. And they went, oh yeah, simpler. Must be about right. Makes sense. Quite often the simpler one is the better one. Copernicus' theory simplified the model of the solar system tremendously. Furthermore, a good scientific theory has explanatory powers that cover a broad scope. It explains a lot, even phenomena that it was not intended to explain. The scope or the range of a good theory also extends to bold predictions, like Einstein's theories. I've really given you a whole lot of stuff to think about here. I understand that. And I'm talking lots. I also get that. Unfortunately, some days are just like that. Often these predictions, such as Einstein's prediction that light would bend near large bodies as the sun's light travels through space, around large bodies, large planets, the light rays actually bend, which leads us to believe, does light have matter? Like when you look, over here in the light side, over here on Tia's side, we're being bombarded by light. Does she get whacked in the head by light particles? Do you feel it? No. I don't feel it. There's no particles there. Right? If I turn the lights out, can you see the light bend around the door? No. That light's still on, but you can actually see, if you look at the port, you can see the light bending around the door. You can. If you've been to the pool when they have the wave, I can see it. If you've been to the pool when they have the waves on, do they still have the waves in the pool on? Yeah. Yeah? I haven't been to the pool in a long time. Do the waves bend around the barriers in the pool? They absolutely do, because waves are a wave, and that's what waves do. Waves bend around things. Guess what light is? Also a wave, and it bends around things. And I can show you all kinds of videos, and I can do it in class as well. I'm not going to. Okay? But light also acts like a particle sometimes. It actually is bombarding you at the head. You just can't feel it, they're really, really small. But if you've got a lot of gravity, like a big giant planet, it will actually bend the light. So light acts as a wave and a particle. That's the theory. Is it true? There's a lot of evidence for it. There's a lot of evidence for it. Oh, that was a lot of talk. Is it harder to listen to all that, or is it harder for me to stand up here and talk through it all? It's pretty hard. I understand. I sat through sessions yesterday. When I go to a really loud PD session, where the guy just going, I sit there and I go, well, this is how students feel someday. So I know how you feel. I try not to be that guy who goes, which is exactly what I just did. Exactly. Okay. You have one more page, right? I promise that the reading level. No, I promise that the reading level on this one is lower, more in line with what you're used to. So I'm going to go do my test because I've taken my laptop, so I've got to go get it done. I would encourage you to read, and then there are 6 questions there. I'm not going to say you got to do them, but that's what you got to know by the end of this, right? So read, summarize your thoughts there. I'll give you a few minutes, and then I'm going to tell you a story about Clever Hans, the smart horse. Okay, I'll give you some time. Yeah. Here's the story of Clever Hans. It's a good example of what's called the law of parsimony, or Occam's razor. And I don't know if I'm actually pronouncing Occam right. Okay? But here's how it goes. Not all explanations for a knowledge claim are created equal. Some explanations involve more details and make more assumptions than others. In other words, they're more complicated. Some theories are more complicated. Assume you were confronted by 2 explanations for the same phenomenon, for the same event. Both explanations seem equally plausible. What does that mean? Plausible. It means that it's possible, or likely, right? Which one would you select? The one that involved numerous assumptions and details, or the one that involved fewer assumptions and details? The complicated one, or the easy one? The easy one. If common sense tells you to select the explanation that makes the fewest assumptions, remember assumptions also require explanations, then you already have a good understanding of the law of parsimony. Here's an old but excellent example of the law of parsimony. In the early 1900s, a gentleman by the name of Mr. Wilhelm von Osten, a retired mathematics teacher, owned a remarkable horse named Clever Hans. Hans became world famous. This is the true story. Became world famous because he could apparently solve mathematical problems that involved decimals, fractions, tell time, and read, among other remarkable abilities. He had a pretty smart horse. For example, someone, his trainer as well as strangers, might ask Hans what 7 divided by 4 equals. And Hans would tap the answer out with his hoof, like so, and receive a treat when he was correct, which was well over 90% of the time. That's pretty good. A committee that included the noted German psychologist Karl Stumpf was appointed by the German government to study this phenomenal horse and prove that his so-called abilities were nothing but a hoax. The committee completed their task and reported that although they were unable to prove that Hans was receiving intentional cues, they remained unconvinced that he was able to solve such mathematical problems and complete the remarkable feats by using his cognitive process. In other words, they thought that someone was giving the horse cues to stop tapping his foot, but they couldn't prove it, but they didn't believe that the horse was actually that smart. They didn't think it was possible. Stumpf's assistant, Oskar Funst, decided to continue investigating the phenomenal horse. Fuchs conducted several experiments and concluded that when Hans could see the person asking the questions, he was able to supply the correct answer. Okay, so if I'm the horse, and Jason asks me the questions, I can answer them. But when the horse is turned so they can't see, the horse can't do it. Okay? If Hans could not see the person asking the questions, then his performance fell to near 0 levels. He couldn't do math when he couldn't see the person that was asking the question. What does that tell you? The horse is really smart? Doesn't make sense, does it, right? Fuchs was faced with 2 alternative explanations for the horse's abilities. Either, 1, Hans understood the question, was able to use the cognitive processes, his brain, but only when he was able to see the questioner for some reason to solve the problem. Or the person was asking the question was somehow inadvertently cueing the horse when to stop tapping at the appropriate moment. Which one of those is the most likely, the simplest explanation? Number 2. Somehow the person was telling the horse when to stop tapping, not the horse was smart. Applying the law of parsimony, Fuchs chose the latter explanation, the second one, and persisted in his investigations. He finally determined that almost everyone who asked questions of Hans made a minute upward movement of their head when the correct answer was reached. So, the person asks the horse the question, says what's 7 divided by 4, the horse starts tapping his foot, and just as he gets to the right answer, the person does what? Because they're getting anxious, right? Ooh, the horse is going to get it. They get all excited. Their face lights up. I'm exaggerating, right? And the head goes up, and the horse recognized that and knew that that meant stop tapping your hoof. Okay? This was an instance of positive reinforcement, not smart horses. If you apply the law of parsimony as you evaluate knowledge claims, you are well on your way to becoming a good psychological consumer. Some initial points to consider, blah, 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 don't care. Okay? So what is the law of parsimony? It should be on the board too, something still at the end of the day. What is the law of parsimony? If you're given more than one explanation, which one should you pick? Simple one. Keep it simple. Principle. Excellent. We're done. 5 minutes to relax before you go off on your extended lunch break, maybe. What? Oh, thanks, man.